The write-ahead log rotation subsystem manages sequential log file transitions as they reach defined size thresholds. When an active log segment accumulates data beyond the configured max segment bytes parameter, the system initiates rotation by closing the current segment, flushing all pending writes to disk, and creating a new active segment with an incremented sequence identifier. This process ensures bounded disk usage while maintaining complete transaction durability. Log segments are identified by a monotonically increasing sequence number embedded in the file name structure. The naming convention follows the pattern while segment sequence start offset.log, where start offset denotes the byte position within the logical transaction stream where the segment begins. This dual identifier approach enables rapid location of segments covering specific transaction ranges without full directory traversal or metadata lookups. Rotation events are triggered by either volume-based thresholds or time-based intervals. The volume threshold parameter max segment bytes defaults to 268,435,456 bytes. The time-based rotation setting rotation interval minutes, when non-zero, forces segment closure regardless of fill level once the specified duration elapses. Both conditions are evaluated independently, and whichever condition satisfies first initiates the rotation cycle. During active rotation, a two-phase transition occurs. Phase 1 acquires an exclusive lock on the log writer state, ensuring no concurrent writes to the current segment. Phase 2 initiates synchronous disk flush of all buffered data, invoking fsync at the operating system level. Only after fsync reports success does the system release the writer lock and proceed to segment creation, minimizing the window where data loss is theoretically possible. Completed log segments transition to archival candidates once they are no longer referenced by recovery operations or active readers. The archival system evaluates segments based on their sequence number and last access timestamp. Segments older than the checkpoint LSN plus min retained segments are eligible for archival. This retention policy balances recoverability against storage efficiency by maintaining configurable overlap between archived and active log files. Archive format compression is applied through configurable codec selection. Supported codecs include identity for uncompressed storage, deflate for moderate compression ratios, and ZSDD for higher compression with bounded decompression overhead. The archive codec parameter specifies the selected codec at archive time. The codec identifier is stored in a header field within each archived segment, enabling automatic decompression during recovery without external configuration hints. Compressed archive segments are prefixed with a fixed-width binary header containing segment metadata. The header format includes an 8-byte magic value for format validation, a 2-byte version number for schema evolution, and 4 bytes specifying the original uncompressed size. The codec identifier occupies 2 bytes, followed by a 4-byte CRC32 checksum computed over the entire compressed payload. Recovery operations locate required segments through index, metadata maintained separately from the log files themselves. The recovery segment index structure stores entries mapping transaction log sequence numbers to segment identifiers and their storage locations. When recovery initiates, it loads the index into memory and performs binary search to identify the first segment covering the target recovery point, substantially reducing disk I/O compared to sequential scanning. Segment metadata persists in a separate control file updated after each successful archival. The control file contains a list of archived segment records, each storing the segment sequence number, original size, compressed size, codec, CRC32, timestamp, and storage location path. This persistent record enables recovery initialization without enumerating the archive directory, accelerating system startup when large archive repositories exist. The archival process executes asynchronously within a dedicated background thread pool. The archive worker threads parameter specifies the number of concurrent archival operations. Each worker monitors a queue of segments eligible for archival and processes them independently. This design prevents blocking the active log writer and enables efficient utilization of compression, CPU overhead on multi-core systems. Failed archival operations generate error events logged to the system event stream with severity error. The archival retry mechanism respects exponential backoff starting at initial retry interval seconds with a multiplier of 2, capped at max retry interval seconds. If archival fails beyond max retry attempts, the segment remains in the active log area until manual intervention or storage capacity pressure forces cleanup. Log segments may be retrieved from archive during recovery, if the current active segment set lacks coverage for the required transaction range. Retrieval decompresses archived segments using the codec specified in the segment header. The decompressed data is validated against the stored CRC32 before integration into the recovery pipeline. Decompression failures trigger recovery error handling and may necessitate recovery point advancement. Archival storage may target local file system paths or external cloud object storage systems. The archive storage backend parameter specifies the target location. When configured for local storage, segments are written directly to the specified directory path. For cloud storage, the system constructs object keys using the segment sequence number and uploads through the configured cloud provider API with configurable authentication and retrievable transports. Archive retention follows time-based and count-based policies applied independently. The archive retention days parameter specifies the minimum age in days before segments become eligible for deletion. The archive retention count parameter specifies the minimum number of most recent segments to retain regardless of age. Deletion occurs after both conditions are satisfied, preventing accidental loss of segments required for compliance or extended recovery scenarios. Archive deletion operations execute within the background worker thread pool using the delete archived segments task type. Segments are deleted sequentially in reverse chronological order once deletion criteria are satisfied. Deletion failures are logged but do not block subsequent deletions. File system space reclamation may be delayed by operating system behavior and periodic file system maintenance rather than occurring immediately after deletion. Monitoring integration exposes archive metrics through standard telemetry channels. Counters track archival operations total and deletion operations total across all worker threads. Gauges expose active archival queue depth and archive storage used bytes. Histograms record archival latency MS and decompression latency MS for performance analysis. These metrics enable operators to validate archival throughput and identify storage growth patterns requiring manual intervention.